Welcome to the lesson on the collection and presentation of data. At the end of this lesson, you will be able to appreciate the importance of the collection of data and distinguish between primary and secondary data. You will also be able to define frequency of data and arrange the given data in ungrouped and grouped frequency distribution tables. Delhi records hottest day in 20 years. Biggest fall in Sensex in 5 years. Afridi scores the fastest century in one-day cricket history. India's population to overtake China by 2030. You must have seen these headlines in newspapers. Have you ever wondered what makes such headlines possible? These headlines are possible only because some people or organizations are continuously maintaining a record of quantities, like temperatures of different cities, the rise and fall of Sensex, scores of different batsmen in different matches, or the population of India. A systematic record of facts or different values of a quantity is called data. Such records or data is collected over a period of time and continuously updated. Data is collected with a specific purpose in mind. However, the analysis of data can give us many different kinds of information. For example, data collected in a population survey in a state not only tells us about the total population of the state, but also the number of male and female residents and the male-to-female ratio in that state. Data is not just about population surveys or cricket scores. Data is continuously being collected all around us through scientific experiments, opinion polls, election results, satellite images, and much more. Even your report card is just a collection of data about your year-round performance. All this data not only helps us keep track of current happenings and trends, but also helps us predict what might happen in the future. The school authority wants to deploy a school bus for their students coming from a particular locality. Our friend here is assigned a project to find out how many children in the school come from that locality. Now, how would he collect this data? One way to collect this data is that he personally speaks to every child in each class to find out where that child lives. The data collected personally by him is called primary data. Primary data can be collected through questionnaires, interviews, observations, case studies, portfolios, etc. It is quite difficult and time-consuming. A far easier way for our friend would be to approach the school authorities and get the names and addresses of students coming from that particular locality. The data gathered from a source where it already exists is called secondary data. You can see that collecting secondary data is far easier than collecting primary data. Mrs. and Mr. Longlife are both in their 90s, and they have a happy joint family. A rather large happy joint family. Let us look at the ages of all the members in this family. It would be interesting. As you can see, the data of ages of the different members of Mr. Longlife's family is quite an interesting mix. Can you notice the ages of the oldest and youngest members of the family? Let us see if we can present the data to make this observation easier. We can make the observation of highest and lowest values in given data easier by simply arranging the data in ascending or descending order. Here, we have arranged the ages of Mr. Longlife's family members in descending order. The highest and lowest values in the given data are of special importance. The difference between them gives a number that is called the range of given data. Here the range of the given data is 91. Meet Mr. Pinch Hitter. Sadly, he's not in the best of forms this season. Here he goes again for a duck. Have a look at his scores in the last 15 innings. Can you immediately notice how many ducks he scored? Let us see if there is a better way to present this data. Now, on arranging the given data in a tabular form, it's clear. Mr. Pinch Hitter was out for 0 5 times in the last 15 innings. He got out after scoring 2 runs in 2 innings, 9 in 1 innings, and so on. Note the second column on this table shows the number of times a value occurs in the given data. This is called the frequency of that value of data. For example, here the frequency of 0 is 5 and the frequency of 16 is 3. Remember, this table was created to present Mr. Pinch Hitter's scores in the last 15 innings. Since this table shows the frequency of different values in given data, it is called a frequency distribution table. The frequency distribution table shown here gives the frequency of each individual value in the given data. It is called an ungrouped frequency distribution table. Is there any other type of frequency distribution table? Let's find out. Now, consider Mr. Pinch Hitter's scores in the last 45 innings. If we make a frequency distribution table like the one we made before, it would be a long table and difficult to read. When we deal with large amounts of data, we create what we call grouped frequency distribution tables. Let's take a look. Now, what have we done here? We have grouped the scores into classes like 0 to 9, 10 to 19, and so on. Note that this table does not show a frequency of individual values of data, but of groups of values. Each group has a fixed number of values. A table that shows the frequency of groups of values in given data is called a grouped frequency distribution table. You can see from this table that Mr. Pinch Hitter has reached scores in the 40s 10 times in the last 45 innings, but hasn't hit a half a century. Guess he needs more net practice. Okay, coming back to our grouped frequency distribution table. The groupings 0 to 9, 10 to 19, and 20 to 29, etc. that we use to group the values in given data are called classes or class intervals of the frequency distribution table. Note that each of these classes contain a fixed number of values, which is 10. The number of values each class contains is called the class size or class width. Now look at a particular class. Say the first one, 0 to 9. The lower value in a class is called the lower class limit, while the higher value in the class is called the upper class limit. Can you identify the lower and upper class limits in the class 0 to 9? Yes. 0 is the lower class limit and 9 is the upper class limit for the class interval 0 to 9. Tally marks are also used to represent frequencies of different values in a frequency distribution table. Tally marks is a system of writing numbers using bars. These bars are grouped into sets of 5. Observe how 2 such sets and 2 vertical bars are used to represent the number 12. Here is a frequency distribution table showing the marks obtained by students in a maths Olympiad. A total of 60 students appeared. 59 students have fitted very nicely in this table. What about the one who got 85.5 marks? Where does she fit in? To fit in her marks, we need to change the class intervals of this table. Let us see how this is done. To change the class intervals of a frequency distribution table, the first step is to consider any two successive classes in the table. Here, let us consider the classes 81 to 85 and 86 to 90. The second step is to find half of the difference between the upper class limit of the previous class and the lower class limit of the succeeding class. Here, this difference between 86 and 85 is equal to 1. Half of this difference is 0.5. Now, rewrite all the classes by subtracting the result of step 2 from the lower class limit and to the upper class limit of each class in the table. See how the table changes. The problem is still not fully solved. Note that 85.5 appear in two classes of the table. So where does this student's marks fit in? In such cases, by convention, we include the twice occurring value in the class interval where it forms the lower class limit. Thus, 85.5 will be included in the class 85.5 to 90.5 and not 80.5 to 85.5. Welcome to the lesson on the graphical representation of data. At the end of this lesson, you will be able to identify the purpose of representing data graphically and identify the different types of graphs that can be used to represent data. You will also be able to draw bar graphs, histograms, and frequency polygons to represent the given data. Mr. Shoestring is looking hassled. His boss wants a report of the monthly sales from last year. Mr. Shoestring has the data in a tabular format. It will take him some time to find the information asked by his boss. But his boss is in a real hurry. Let's help him with this task. You just have 10 seconds to spot the month in which maximum sales were made. Quite difficult, right? If the amount of numerical data is large, interpreting it quickly is difficult. Is there an easier and quicker way to interpret data? Yes, there is. Data can be represented as graphs for quick and easy interpretation. Look at these figures. It is the same data that Mr. Shoestring was struggling with. Identifying the month with the maximum sales can now be seen in a jiffy. Now, the figure we use to represent Mr. Shoestring's sales figures is called a bar graph. A bar graph uses bars or rectangles of the same width but different heights to represent different values of data. Let's see how a bar graph is drawn. Remember Mr. Pinch Hitter, our star batsman. He's going through a bad form. Here are the scores he made in his last 10 innings. Let's draw a bar graph to represent this data. We will use the x-axis and the y-axis to represent a variable and its different values. Here the variable is the number of innings and its value is the corresponding number of runs scored in each inning. We usually use the x-axis to represent the variable and the y-axis to represent its corresponding value. Next, we'll choose a comfortable scale to mark the data in the variables column on the x-axis. For convenience and symmetry, we mark 10 equidistant blocks to represent the 10 innings played by Mr. Pinch Hitter. Let's look at the maximum value in the values of the variable to decide on a suitable scale for the y-axis. Here the values of the variable are the runs scored and their maximum value is 49. Let's choose a scale of 1 unit equal to 5 runs and mark equidistant points on the y-axis to represent a maximum of 50 runs. Next, we'll draw bars for each innings on the x-axis representing the number of runs scored in it as per the scale chosen on y-axis. For example, in the first innings, the score was 16. So a bar corresponding to score of 16 on the y-axis is drawn. For the second innings, a bar corresponding to a score of 18 is drawn on the y-axis. Similarly, we draw the bars for the other innings. But notice that the score is 0 in the 6th and 9th innings, so no bar is drawn. This is the completed bar graph. Note that in the bar graph, the bars have equal gaps between them. The width of the bars does not matter, though we keep it constant for the sake of symmetry. The height of the bars represents the runs scored in each innings. Now, here's another collection of data. In this table, the marks obtained by 60 students in the Maths Olympiad are given. Can you recognize what kind of a table is this? This is a grouped frequency distribution table that has data grouped in continuous class intervals. How do we represent this data graphically? Let's find out. We start by drawing two axes, x and y, as we did while drawing a bar graph. We use the x-axis to represent the variable and the y-axis to represent its value. Here the variable is the marks obtained and its value is number of students. Next, we'll choose a scale to mark the class intervals in the marks column on the x-axis. Let's take 1 centimeter equal to 10 marks. Since there are 6 class intervals, we mark 6 equal lengths of 1 centimeter on the x-axis. Note that since the class intervals are continuous, we will not leave any gap between them on the x-axis. Now, here is something interesting to note. The class intervals in the given table do not begin with 0. This is the reason we marked the class intervals slightly away from the 0 mark. To further indicate this, we make a small kink at the beginning of the x-axis. Always remember to do so when marking values on an axis that do not begin with 0. Next, we look at the maximum number of students to decide on a suitable scale for the y-axis. The maximum value is 16, so we can choose a scale of 1 centimeter is equal to 2 students and mark 10 such points on the y-axis to represent a maximum of 20 students. Next, we draw bars for each class interval on the x-axis representing the corresponding number of students indicated on the y-axis. For example, 6 students scored marks in the class interval 40.5 to 50.5. 14 students scored marks in the class interval 50.5 to 60.5 and so on. This is the completed graph. This kind of graphical representation of data is called a histogram. Note that the bars have no gaps between them. The width of the bars is proportional to the class intervals of data. Since the class intervals have the same width here, all bars have the same width. The heights of the bars represent the frequencies corresponding to the different class intervals. The area of each rectangle is also proportional to its corresponding frequency. Now the school has decided to give honor certificates to all the students who scored above 70.5 in the Maths Olympiad. To show how many students scored the required marks, the data table was modified as shown here. Let us see how a histogram representing this data looks like. You can see that the class intervals are not the same here. Whenever this happens, we need to apply a correction to the height of the rectangle of the unequal class interval. This is necessary so that the area of the rectangle and its height are still in proportion with its correct frequency. Here we have to adjust the height of a class interval with a width of 30 to other class intervals with a width of 10. The calculation is simple as shown here. Thus, the height of the class interval 70.5 and above will be 9.66 and not 29. Now, let's look at another interesting way of representing data. Consider the midpoints of the upper side of all the rectangles in this histogram and join them with a line. Now consider two more class intervals just before and after the given class intervals. Note that we keep the class width constant. Now join the upper midpoint of the first rectangle to the midpoint of the new class interval marked before it. Similarly, join the upper midpoint of the last rectangle with the midpoint of the new class marked after it. What do you get? The figure we get is known as a frequency polygon, corresponding to the given data. The area of a histogram is equal to the area enclosed by its corresponding frequency polygon. Here is a table showing the charges of a courier company for packages with different weights. Let us try and draw a frequency polygon for this data. Let us try and draw the frequency polygon without drawing the corresponding histogram. For this, we have to find what we call class marks for each class interval of weight in the given table. The class mark for a class interval is half of the sum of the upper and lower class limits of the class. For example, the class mark for the class 0 to 20 is 10, and class mark for the class 20 to 40 is 30, and so on. As usual, we start by drawing the two axes, x and y. Here the variable is weight, and its value is the courier charges or rate. Now we mark the class marks found earlier along with the x-axis. Next, we mark the rates along the y-axis. Now, we plot the corresponding rate for each class mark on the figure and join these points. Does that complete our frequency polygon? Not quite. To complete the frequency polygon, we need to join it to the x-axis. For this, consider an imaginary class interval of -20 to 0 before the first class interval given in the table. Join the midpoint of this class interval, that is, -10 on the x-axis, to the beginning of the frequency polygon. Now, consider class interval of 100 to 120 after the last class interval given in the table. Join the midpoint of this class interval, that is, 110 on the x-axis, to the end of the frequency polygon. This completes the required frequency polygon. Welcome to the lesson on measures of central tendencies. At the end of this lesson, you will be able to define the mean, median, and mode of data. You will also be able to calculate the mean, median, and mode of the given data. Meet Mr. Pinch Hitter. Sadly, he's not in his best of forms this season. Here he goes again for a duck. Here are the runs that were scored by him in the last 15 innings. The cricket season is ending, and Mr. Pinch Hitter has to submit a performance record. He can do it in any of the three ways listed on this form. Mr. Pinch Hitter would obviously want to make a good impression. Let us find values for these three quantities and see which one Mr. Pinch Hitter would like to use. First, let us find the average score of Mr. Pinch Hitter in his last 15 innings. Here are the scores made by Mr. Pinch Hitter in his last 15 innings. Now, his average score is equal to the sum of the scores made in all the innings divided by the number of innings played. Let us calculate. The sum of all the runs scored by Mr. Pinch Hitter in 15 innings is 209. Dividing this total by the number of innings, that is 15, we get his average score in 15 innings as 13.93. The average score of Mr. Pinch Hitter also represents the mean of the scores made by him in the last 15 innings. The mean of a given set of values is equal to the sum of all the values divided by the total number of values. The mean of a given set of values is represented by the expression shown here. Here x with a bar over it represents the mean of n number of values. xi with a summation sign denotes the sum of values of x from its first to nth value. Let us apply this equation to Mr. Pinch Hitter's case. In both methods that we have used so far to calculate the mean, we have added a large number of values. This would be more problematic if we were to using data from, say, 30, 50, or 100 innings. Let us see if there is a simpler way to calculate the mean. Let us arrange Mr. Pinch Hitter's scores for the last 15 innings into a frequency distribution table. Now, let us see how this helps. Here the mean x bar is equal to the sum of the products of different values of x and their respective frequencies divided by the sum of all the frequencies of the different values of x. Let us apply this formula to verify the value of the mean we calculated earlier. We see that the value of the mean agrees with the value we calculated earlier. So, we have found the value of the first quantity of Mr. Pinch Hitter's performance record. Now, let us find the value of the second quantity. Now, let us find the middle score of Mr. Pinch Hitter in his last 15 innings. To find the middle score, we arrange his scores over 15 innings into ascending order. Now, let us find the value that lies in the middle of these numbers. In this case, we see that this value is 9. The value that lies in the very center of a given set of values arranged in ascending or descending order is called the median of the given data. If the number of the given values is odd, as in this case 15, the median is given by the formula shown here. By the formula, the median of this group of values is the 8th value or the number 9. Now suppose we were considering Mr. Pinch Hitter's scores of only 14 innings. Let us see if the median remains the same. We see that there is no middle value here. How do we find the median in this case? If the number of the given values is even, as in this case 14, the median is the mean of the two middlemost values, which is given by the formula shown here. By the formula, the median of this group of values is the mean of the numbers at the 7th and 8th position of 5.5. So we found the values of the first two quantities. Now let us see how he fares with the third quantity. Now, let us find the number of runs that Mr. Pinch Hitter has scored the most number of times in his last 15 innings. Here are the scores made by Mr. Pinch Hitter in his last 15 innings. Is there a quick way to spot the runs scored most often? A frequency distribution table may help. Now, there is no confusion. Clearly, Mr. Pinch Hitter has scored a 0 the maximum number of times in his last 15 innings. The value that occurs the maximum number of times in a given set of values is called the mode of the given data. Here the mode is 0. Well, we have found the values for all the three quantities in Mr. Pinch Hitter's performance record. Which of these three values do you think he would like to use? Do you think that an average score would always give him the best value to present? Let's find out. Mean, median, and mode together are called the measures of central tendencies of data. They help us to better interpret data, but they are affected by the distribution of data and thus should be considered with other information. Now, suppose the scores of Mr. Pinch Hitter in the last 15 innings are as shown here. Which central tendency would he choose this time to project a good performance? In this case, the average score or mean is 11.73. The middle score or median in this case is 7. The run scored the maximum number of times or mode in this case is 49. Would Mr. Pinch Hitter still prefer to use his average score or mean in his performance record? Not likely. This time he would prefer to use the mode. Thus, we can see that the central tendencies of data depend on the distribution of values and must be considered with other information for effective interpretation of data.